Today we're diving into the world of databases, a foundational technology that powers everything from your favorite apps to major business systems. Databases are organized collections of data, designed for efficient storage, retrieval, and management. Whether you're aware of it or not, you interact with databases every day, from checking your bank balance to scrolling through social media. In this video, we'll break down the essential concepts behind databases, making them easy to understand for beginners and providing a solid foundation for further learning. Let's start by exploring what makes databases so important in our digital world. Database is more than just a digital filing cabinet. It's a structured system for storing information in a way that makes it easy to find, update, and manage. Think of it as a highly organized library where every book, page, and word is cataloged for quick access. Databases can store all kinds of data: numbers, text, images, and more. They're used in countless applications, from online shopping carts to hospital records. The structure and rules that govern how data is stored and accessed are what set databases apart from simple data storage methods. There isn't just one kind of database. In fact, there are several types, each designed for different needs. The most common is the relational database, which organizes data into tables with rows and columns. There are also nosql databases, which handle unstructured data and are popular for big data and real-time web apps. Other types include object-oriented, hierarchical, and network databases. Each type has its strengths and is chosen based on the specific requirements of a project or organization. Relational databases are the backbone of many business systems. They store data in tables, much like a spreadsheet, with rows representing records and columns representing attributes. Relationships between tables are established using keys, allowing for complex queries and data integrity. Popular relational database systems include MySQL, PostgreSQL, and Oracle. These systems are known for their reliability and ability to handle large volumes of structured data efficiently. NoSQL databases are designed for flexibility and scalability. Unlike relational databases, they don't rely on tables and can store unstructured or semi-structured data. This makes them ideal for applications that handle large volumes of diverse data, like social media platforms or IoT devices. Examples include MongoDB, Cassandra, and Redis. NoSQL databases are often used when speed and the ability to scale horizontally are more important than strict data consistency. Database Management System, or DBMS, is the software that interacts with end users' applications and the database itself to capture and analyze data. The DBMS handles tasks like data storage, retrieval, security, and backup. It ensures that data is consistently organized and easily accessible. Examples of DBMS include Microsoft SQL Server, MySQL, and MongoDB. The DBMS is a crucial layer that makes working with databases practical and efficient. Relational databases, data is organized into tables. Each table contains rows called records and columns called fields. For example, a customer table might have columns for name, email, and phone number, with each row representing a different customer. This tabular structure makes it easy to sort, filter, and analyze data. Understanding tables and records is fundamental to working with relational databases. Each column in a database table is called a field, and each field has a data type. Data types define what kind of data can be stored, such as text, numbers, dates, or even images. Choosing the right data type is important for data integrity and efficient storage. For example, storing a date as text can lead to errors, while using a date data type ensures proper sorting and calculations. Primary key is a unique identifier for each record in a table. It ensures that every row can be uniquely distinguished from others. For example, in a student table, a student ID might serve as the primary key. Primary keys are essential for maintaining data integrity and enabling relationships between tables. Without them, it would be difficult to manage and reference specific records. Foreign keys are used to link tables together. A foreign key in one table points to a primary key in another, creating a relationship between the two. For example, an order table might have a customer ID as a foreign key, linking each order to a specific customer. This allows for complex queries and ensures data consistency across related tables. Indexes are special data structures that improve the speed of data retrieval operations. Think of them like an index in a book, which helps you quickly find the information you need. By creating indexes on certain columns, databases can search and sort data much faster. However, indexes also require additional storage and can slow down data updates, so they must be used wisely. Normalization is the process of organizing data to reduce redundancy and improve data integrity. By breaking data into related tables and defining relationships, normalization ensures that each piece of information is stored only once. This makes updates easier and reduces the risk of inconsistencies. While normalization is important, sometimes denormalization is used for performance reasons in certain scenarios. Normalization is the opposite of normalization. It involves combining tables or duplicating data to improve read performance. While this can speed up data retrieval, it may introduce redundancy and potential inconsistencies. Denormalization is often used in data warehousing and analytics, where fast query performance is more important than strict data integrity. SQL, or structured query language, is the standard language for interacting with relational databases. With SQL, you can create tables, insert data, update records, and retrieve information using queries. SQL is powerful and widely used, making it an essential skill for anyone working with databases. Its syntax is designed to be readable and expressive, allowing users to perform complex operations with relatively simple commands. CRUD stands for create, read, update, and delete, the four basic operations you can perform on data in a database. These operations are fundamental to managing any database. For example, adding a new customer is a create operation, viewing their details is read, updating their information is update, and removing them is delete. Mastering CRUD operations is essential for effective database management. Transaction is a sequence of database operations that are treated as a single unit. Transactions ensure that either all operations succeed or none do, maintaining data consistency. For example, transferring money between bank accounts involves debiting one account and crediting another, both must succeed together. Transactions are governed by the ACID properties, which we'll discuss next. ACID stands for atomicity, consistency, isolation, and durability. These properties ensure that database transactions are processed reliably. Atomicity means all operations in a transaction are completed or none are. Consistency ensures data remains valid. Isolation prevents transactions from interfering with each other, and durability guarantees that once a transaction is committed, it won't be lost, even if the system crashes. Database schema defines the structure of the database, including tables, fields, relationships, and constraints. Think of it as a blueprint for how data is organized and connected. Schemas help ensure that data is stored consistently and can be easily understood by developers and users. Changes to the schema can impact how data is stored and accessed, so careful planning is essential. Data integrity refers to the accuracy and consistency of data within a database. It's maintained through rules, constraints, and validation checks. For example, a constraint might ensure that email addresses are unique or that a date of birth is in the past. Maintaining data integrity is crucial for reliable and trustworthy information. Constraints are rules applied to database tables to enforce data integrity. Common constraints include primary keys, foreign keys, unique constraints, and check constraints. These rules prevent invalid data from being entered and help maintain the quality of the database. For example, a unique constraint ensures that no two users have the same email address. Relationships connect tables in a database, allowing data to be linked and queried across multiple tables. The main types are one-to-one, one-to-many, and many-to-many relationships. These relationships are established using keys and are essential for modeling real-world scenarios, like linking customers to their orders or students to their classes. Entity relationship model is a way to visually represent the structure of a database. It uses entities, things like people or products, and relationships, how those things are connected, to create a diagram of the database. Diagrams help in designing databases and understanding how data is connected. Data redundancy occurs when the same piece of data is stored in multiple places within a database. While sometimes necessary for performance, too much redundancy can lead to inconsistencies and wasted storage. Proper database design aims to minimize redundancy while ensuring data is accessible and reliable. Data consistency means that data remains accurate and uniform across the database. When multiple users or applications interact with the database, consistency ensures that everyone sees the same, correct information. This is especially important in systems where data is updated frequently, like banking or inventory management. Backup and recovery are critical aspects of database management. Regular backups ensure that data can be restored in case of hardware failure, software bugs, or accidental deletion. Recovery processes help bring the database back to a consistent state after a problem. Without proper backup and recovery strategies, valuable data could be lost forever. Database security involves protecting data from unauthorized access, breaches, and other threats. Security measures include user authentication, access controls, encryption, and regular audits. With the increasing importance of data privacy, robust security practices are more essential than ever to safeguard sensitive information. Databases often have multiple users, each with different roles and permissions. For example, an administrator can manage the entire database, while a regular user might only be able to view or update certain data. Assigning roles helps control access and maintain security, ensuring that users only have the permissions they need. View is a virtual table created by a query. It presents data from one or more tables in a specific way without storing the data separately. Views are useful for simplifying complex queries, restricting access to sensitive data, and presenting information in a user-friendly format. They help customize how users interact with the database. Stored procedures are pre-written SQL code that can be saved and reused in the database. They help automate repetitive tasks, enforce business rules, and improve performance by reducing the amount of code sent from applications to the database. Stored procedures make database operations more efficient and consistent. Trigger is a special kind of stored procedure that automatically runs in response to certain events, like inserting or updating data. Triggers can enforce rules, maintain audit trails, or update related data automatically. While powerful, they should be used carefully to avoid unintended consequences and performance issues. Indexing strategies are crucial for optimizing database performance. By choosing which columns to index and what type of index to use, you can significantly speed up data retrieval. However, too many indexes can slow down data updates and increase storage requirements. Balancing indexing is key to maintaining a fast and efficient database. Data warehouse is a specialized database designed for analysis and reporting. It collects data from multiple sources, transforms it, and stores it for easy querying. Data warehouses are used in business intelligence to uncover trends, patterns, and insights. They are optimized for read-heavy operations and large-scale data analysis. OLTP, online transaction processing, and OLAP, online analytical processing, are two main types of database workloads. OLTP systems handle day-to-day transactions like sales or reservations, focusing on speed and reliability. OLAP systems are designed for complex queries and data analysis, often used in reporting and business intelligence. Understanding the difference helps in choosing the right database solution. Replication involves copying data from one database to another, often in real time. This improves availability, fault tolerance, and performance by distributing the workload. Replication is commonly used in large systems to ensure that data is always accessible, even if one server fails. Sharding and partitioning are techniques for dividing a large database into smaller, more manageable pieces. Sharding distributes data across multiple servers, while partitioning splits data within a single database. Both methods help improve performance and scalability, especially for applications with massive amounts of data. Database migration is the process of moving data from one database to another. This might be necessary when upgrading systems, switching vendors, or consolidating data. Migrations require careful planning to ensure data integrity and minimal downtime. Tools and best practices help make migrations smoother and less risky. Cloud databases are hosted on remote servers and accessed over the internet. They offer flexibility, scalability, and reduced maintenance compared to traditional on-premises databases. Popular cloud database services include Amazon RDS, Google Cloud SQL, and Microsoft Azure SQL Database. Cloud databases are increasingly popular for businesses of all sizes. Big data refers to extremely large and complex data sets that traditional databases can't handle efficiently. Specialized databases and tools like Hadoop and Spark are used to store, process, and analyze big data. These technologies enable organizations to extract valuable insights from massive amounts of information. Performance tuning involves optimizing a database to run as efficiently as possible. This includes adjusting queries, indexing, hardware resources, and configuration settings. Regular tuning ensures that the database can handle growing workloads and deliver fast response times for users and applications. Monitoring a database involves tracking its performance, usage, and health. Tools can alert administrators to issues like slow queries, hardware failures, or security breaches. Proactive monitoring helps prevent problems before they impact users and ensures the database runs smoothly. Documentation is essential for understanding and maintaining a database. It includes details about the schema, tables, relationships, and business rules. Good documentation makes it easier for new team members to get up to speed and helps prevent costly mistakes during development and maintenance. Open-source databases are freely available and can be modified to suit specific needs. Popular examples include MySQL, PostgreSQL, and open-source options offer flexibility, cost savings, and a large community of users and developers. They are widely used in both small projects and large enterprises. Proprietary databases are commercial products developed and maintained by companies. Examples include Oracle Database and Microsoft SQL Server. These databases often offer advanced features, dedicated support, and integration with other enterprise tools. Organizations choose proprietary solutions for reliability, performance, and vendor support. Future of databases is exciting, with trends like automation, artificial intelligence, and cloud computing shaping the landscape. Databases are becoming more intelligent, self-managing, and integrated with other technologies. As data continues to grow in volume and complexity, databases will play an even more critical role in powering innovation and decision-making. I've covered a lot of ground in this introduction to database concepts. From understanding what a database is to exploring types, structures, and essential features like security and performance, you now have a solid foundation. Databases are at the heart of modern technology, and mastering their concepts opens up countless opportunities in tech and business. Keep exploring, and you'll discover even more ways databases shape our digital world.